Let us start our lecture today. So in the last class, we were trying to solve this equation. dx over dt is equal to e to the power minus t squared, where x3 is equal to 7. All right? So this is the equation that we were trying to solve last time. So from last time, we know that in order to solve this equation, first you have to know that this is t e to power minus s squared ds plus a constant c, right? So the first step is to integrate both sides of this equation. So this is integrating. All right, so when you integrate both sides of this equation, you're going to get xt will be the integral from minus infinity to t of e to power minus s squared ds plus a constant c. All right? So this x3 is equal to 7 is called initial condition. So the initial condition is the constraint that you put at one point to the solution of the differential equation. All right? So in this case, we have to allow the value at 3 of x to be 7. So this is called the initial condition. So which means that we do not stop here. We have to continue, right? So we have to continue to solve for this constancy, right? So we continue. So we have x3 will be the integral from minus infinity to t of e to power minus s squared ds plus the constant c, right? But we know that this is 3, this is 7, so 7 will be integral from minus infinity to t of e to power minus s squared s plus c, which means that c will be 7 minus the integral from minus infinity to t of e power. So this t should be 3, all right? So because we're gonna replace t by 3 ds, all right? So using the initial condition, you replace the general formula that we obtained from here to here, and you're gonna get 7 is equal to this interval plus a constant c, right? So which means that c will be 7 minus this interval. But this interval is a constant, right? Because this is an interval of an explicit function on an explicit interval, right? So this is a number. This is a number and a constant. All right? So now we're going to use this number and we're going to plug back to x. All right? So x is going to be the integral from minus infinity to t e to power minus s squared ds plus c, but c will be replaced by 7 minus the integral from 0 to infinity of 3 e to power minus s squared ds. All right? So this is the c. So I'm going to replace this c here to the c here, and I'm going to have this formula, right? So now this comes a question that many of you ask me. So I'm going to subtract this integral and this integral. Right? So I'm going to put 7 outside, and I'm going to have minus infinity to t of e to power minus s squared ds minus the integral from minus infinity to 3 of minus es squared ds plus 7. All right, the 7 is going here, and I'm going to subtract the two integrals. What do I get?
Integral of 3 to t.
Right, excellent. So I'm going to get the integral from 3 to t, and the reason, can you sign at the back of the paper, and then you sign the attendance. So I'm going to say that this difference between the two integrals is going to be the integral from 3 to t. And why is it? So this is going to be integral from 3 to t of e to the power minus s squared ds plus 7. All right, so the formula that we use is the following. The integral from a to b of a function fs ds minus the integral from a to c of a function fs ds will be the integral from c to b of the function fs ds. All right? So you minus the integrals of the same function in two different intervals, AB and AC, and at the end you're gonna get the integral from C to B. Why is it? Yes?
Because when you can take the minus sign as a second integral and switch the limits of integration, and then it will be, you'll have an A on the leftmost limit of the bottom limit, excuse me, of the left side integral, and you have an A on the top. On top. And so
then you'll have the B here.
From B on top to C on the bottom of the right side integral.
This is a good observation. Yes, can you sign at the back of the paper, please? So you observe that integral from A to B of fs ds will be minus of integral from B to A of fs ds, right? So you just switch the two limits and you have to change the sign, right? So now you take the sum. So you're gonna take the integral from B to A of fs ds minus the integral from A to C of fs ds. All right? And now you have minus of integral from B to A of fs ds plus integral from A to C of fs ds. All right? So here I have the integral from B to A, and here I have integral from A to C. So I can sum them, and I can have minus the integral from B to C of fs ds. And this is integral from C to B of fs ds. But there is a simpler way to explain this. This is great. This is very good. But there's a simpler way to explain this. This is using the definition of the integral. So someone knows? Yes?
If you draw like a number line, and then you can see that
The area, right?
yeah, the area.
Can you sign the back of the paper, please? So this is a very good answer, right? So so what is the integral? So you have A, you have B, and you have C. So this is the function fs, right? This is the function fs, right? So the first interval will be this area. Right? So this area will be integral from A to B of fs. Yes. Right? So you draw a function. You take the area that form between that function and the axis, and then now inside the interval from A to B, that will be the integral, right? So the area. So the dot area will be the first integral, right? Now the second integral will be this area, right? So right? So now I'm going to do the same. This is the function f. I have to take the integral from A to C, right? So the second integral, the integral from A to C, will be this area. Now you subtract the two area. What do you get? When you subtract the two area, you get this area. Right? And this area will be what? This area will be the last interval. A to B to C, A to B, C to B. Right. So area. Right. So I explain again. So to see this formula, this is very simple, right? So the first one is the integral from A to B of the function fs. What is it? This is nothing but the area of the shape that forms when you draw this fs and axis, and you draw the two lines A and B. So this is the first interval, right? The second interval will be the area of the shape that form when you draw the function ms and the axis, but you restrict that into the two lines A and C, right? So this is the second interval. So you subtract the two areas, and you get this this one, which is the interval from C to B of fs/ds. Screen questions? All right. So finally, this is the answer that we have. So you have the interval from 3 to t of e to power minus s squared ds plus 7. It's clear? Questions? Right. So now let us go to another example. Right, so in the beginning of lecture 1, what we see is the application of differential equation in population dynamics, right? So we study the population of DC, and we see that this is growing, and this is a differential equation. So now we're gonna learn something, another application, which is in mechanics. So this is mechanics. All right, so this is a very simple example. You have a mass m, right? So you have this mass, right? And so you consider, suppose that here at time 0 is located at the position x0, right? So at time 0, the mass is located at x0, right? So you have a mass which is located at x0, and this is moving, right? So this mass is moving. At position at time t will be located. We denote the position of the mass at any time t to be x, right? So the mass is moving. The mass is moving. Is moving with velocity Vt, right? So this is Vt. So the velocity is changing, right? So it's not a constant, it's changing. So I explain again. We have a mass, m. At time 0, it will be at position x0. At time t, it will be at position xt, right? So this is moving with velocity xt, Vt, right? V depends on t, all right? Now, what is the relation between V and x? Between V and x. Yes?
To use the derivative of x.
Excellent, right? Can you stand at the back there? So V, t will be x prime t. All right? So the velocity will be the derivative of the velocity. So the velocity measure the change in time of the distance that the mass is moving. Now we have another quantity, which is the acceleration. right? So this is at. So what is the acceleration? Yes?
Acceleration is b prime or x double prime.
Excellent. Can you say the back of the paper, please? So the acceleration will be b prime, and this is also x double prime. All right? It's clear? Yes?
I have the paper.
Oh, it's great. Thank you. All right, so I explain again. So I consider mass m, which is moving with velocity vt. At the initial time, it's going to be as x0, and at time t, it's going to be at position xt. So there are two quantities that we want to know. The first one is the velocity, and the second one is the acceleration, right? So why is it moving? This mass is moving because there are forces, right? So you have F1, F2, Fk, right? So the mass is moving. It's not just because it's moving. There should be some force acting on them, on the mass, right? So I call F1, F2, Fk to be the force. F1, F2, Fk, forces acting on M. All right. So the forces acting on M will be called F1, F2, Fk. Now there's a law of Newton, which is the Newton law, which is Newton's second law. Second law. So what is Newton's second law? Yes?
F equals ma.
Yes. Can you say at the back of the paper, please? So the Newton second law will says that, okay, you have ma, then this is equal to the sum of the f, right? Is clear questions? So I explain again. So this mass is moving with velocity v, acceleration a, because there are a lot of forces acting on the mass m. So I call it F1, F2, Fk. By the Newton's second law, m of a will be F1, F2, Fk. All right? Questions? Now I gonna. All right. So now let us suppose that the mass is falling. So if the mass is falling, in the case that the mass is falling down, the only force is the gravity. Right? So in the case that I take the mass and I drop it, right? So like this. So the only force that is acting on this pen is the gravity, right? So the gravity, I denote that by G. So I'm gonna have ma is equal to G. So how do we compute the gravity? The gravity, yes?
The force of gravity is the mass of the object times g, which is the acceleration due to Earth's gravity.
Excellent. Excellent. Can you sign the pineapple paper, please? So if this is going to be m times g, which is a constant, which is 9 point something, 9.8, right? So the gravity will be computed by multiplying m with a constant, which is 9.8, right? This is mass meter per second. So now in this case, you're going to have a is equal to g, right? The acceleration will be equal to this constant. Questions? So now I'm going to say that this is, so suppose that I drop the direction, so I'm going to have a is equal to g. g, which is 9.8, approximately. Now, I said that this is the differential equation. Why? Any other? Yes?
Because we know that A is the derivative of velocity equation.
Excellent.
Derivative of
Yes, can you say it on the paper, please? So now, this is a differential equation. So this is a differential equation because A is V dot and V dot is x2 dot, right? So I normally we said that x dot will be x prime and x second dot will be x second. So this is the notation, right? So sometimes we denote the derivative by a dot or 2 dot as well. So it's the same with the prime. All right, so I explain again. So in this case, A is equal to G. G is a constant, which is approximately 9.8. Because A is the first derivative of the velocity, so we have V dot is equal to G. And also, we have x second dot will be equal to G. And we have to solve this equation. So solving the equation, x2 dot is equal to G. So let me explain again. So suppose that I have a mass, right? The mass is falling down. So the only force that is acting on this mass is the gravity, which is computed by m times g, right? By the Newton's second law, we have ma will be the sum of F1 to Fk. In this case, there is only one force, which is mg. So we have A is equal to G. Because A is equal to G, A is the first derivative of V, and this is also the second derivative of x. All right. So we have two differential equations. We have one differential. So we have one differential equation for V, and we have one differential equation for x. So let us try to solve the equation for x. Right. So we have x2 dot is equal to G. So this will be a differential equation of t. How can we solve this equation? Yes?
Integrate.
Right. Can you sign the back please? So because x2 dot is equal to G, right? So x dot will be the integral from minus infinity to t of G ds plus C. All right? So the first thing that we do here is to take the first integration, right? So in this case, x second is equal to G. What I do is I integrate both sides. I'm going to have x dot is equal to the integral from minus infinity to t of G times s ds plus C. So G is a constant. So what is this interval? T, right? GT. So this is GT plus C. So x dot T will be GT plus C. Our VT is also GT plus C. All right. So in the first integration, what I get is the velocity, right? So I have x second is equal to G, meaning that x dot is integral from minus infinity to G of G plus a constant C. So this is a constant, right? This is a constant. So this gives me GT plus C. So which means that VT is GT plus C. But I still want to find x. How do I find x? Yes? Can you send it back up, please? So now I'm going to integrate it again. So I'm going to have xt will be integral from 0 to t, from minus infinity to t of gs plus c ds. But then I have to introduce a new constant, right? Every time I integrate, I have a new constant. So the first one will give me gt squared over 2, and the second one will give me ct, and then I have c tilde, right? So I'm gonna get xt is gt squared over 2 plus ct plus c tilde. It's clear? Questions? So I explain again. So from the previous argument, we know that A is equal to G. A is equal to G means that V dot is equal to G, and also we have x2 dot is equal to G. Now because x2 dot is equal to G, I can find x dot by integrating both sides. So I have x dot is integral from minus infinity to t of G ds plus C. G is a constant, so this integration is explicit. So I have x dot is going to be gt plus C. In other words, Vt will be gt plus C, right? I'm gonna integrate again to find x. So I'm gonna integrate both sides of this guy, and then I have to add a constant, right? So what I get is g t squared over 2 plus ct plus c tilde. Questions? It's clear? All right, so basically we've just, by this example, we know that, okay, differential equation is also applicable in classical mechanics, all right? And then it's also applying in quantum mechanics and all kind of things that you can think of, like AI or machine learning. Now the application of differential equation are very huge. Right. So now, so let us continue with another techniques to solve differential equation. Right, so 1.3. So this 1.3 is the 1.3 that we have in the book. So I follow the note, the index of the books. All right. So this is 1.3. First order differential equation. First order separable. Differential equation. So what is the meaning of separable differential equation? So in the previous lecture, we know that, okay, how do we solve this guy? So in order to solve this guy, what we do is just integrating, right? To solve, we just have to integrate, right? So we're going to have xt is equal to the integral from minus infinity to t of fs ds plus a constant. Right. So this is what we have. This is what we have for this kind of equation, right? So this is the simplest one that we learned in the very first day. Now, what happens if we have an axiom? All right. So if we have an axiom, we cannot integrate anymore, right? Because when we integrate, we're going to get what? We're going to get the integral from minus infinity to t of fs xs dx plus a constant c. So there's an x here, right? So when you integrate both sides of this equation, you're gonna be stuck because there's an x inside on the right hand side, and there's an x on the left hand side, right? So this is the difficulty. All right, so the method of integration works only for the simplest case in which on the right hand side you don't have x. Right, so here you don't have x. You don't have x in f. But if you have x in f, when you integrate both sides, you still have x on both sides, and you don't know how to do it. So this is why there's a new class of differential equation which is separable, which is called separable. And the separable differential equation is the following one. So if ftx is gt times sx, then we can solve. All right. So in the case that f is the product of a function of t and a function of x, then we can solve. And this is called separable because f can be separated into g and h. Separable means that ftx can be separated, split into g and h. All right? So I explain again. In the very first lecture, we know how to solve dx over dt is equal to ft because in this function, you don't have x in f. You don't have x in f, so you can integrate both sides. And on the right hand side, you don't have x. On the left hand side, you have x, right? So here you have x. And here you don't have x. So which means that x, the solution will be the integral on the right hand side. So this is the simplest one. Now, the more complicated one will be when f depends on x. When you have f depending on x, then when you integrate both sides, on the left hand side you have x, and on the right hand side you have x. So you cannot take x out. You don't know what is the form of x, right? So this is why we have to study a special form of f. So in the case that f is the product of a function of g, of t, and a function of h, this is also solvable by the method that we are going to learn. This equation is called separable because f can be split into two terms. One is g of t, and one is h of x, right? So how do we solve this kind of thing? So let us try to understand one example. So you have in this case dx over dt is equal to x squared cosinus of t. All right. In this case, ftx will be x squared cosinus of t. So this will be hx and this will be gt. Right. So x and t are separable. Right. So for this kind of equation, how do we solve? Yesterday, so
You'll separate dx dt so that dt is on the same side as cosine of t and x squared on the same side of dx.
and you?
Yeah, I was gonna say divide by x squared.
Yes. Can you both sides at the back of the bracket? This is a very good method. All right. So what we do is we separate x and t. We don't put them together, right? So in this case, you have what? You have dx over dt is x squared cosinus of t. So we're gonna separate x and t. So what I do is I'm gonna divide x to here and I multiply dt here. All right. So I'm gonna have dx divided by x squared, and here I put dt up there. I have dt cosinus of t. So x and t are separated. Right? So I explain again. So here I have dx over dt is x squared cosinus of t, right? So the good thing of this is the function f has x squared times cosinus of t. So they're split. So what I do is I divide both sides by x squared. So I divide x squared here, so I get x squared. I multiply dt up there, so I have dt cosinus of t. I get this equation. I have dx over x squared is dt cosinus of t. Right? So now what should I do? Yes?
Integral of both sides.
accent. Can you say at the back of the paper, please? So now what I do is I integrate both sides. Is cosinus t dt, right? Which means that I'm going to take the antiderivative of both sides. So what is the antiderivative of 1 over x squared?
Negative 1 over x.
Yes, can you say it? So I have negative 1 over x. And what is the antiderivative of cosinus t? Yes?
Sine t plus.
Okay. Can you say it back? So you're going to have sinus of t. And of course, you have to have a plus c on both sides. Basically, I have a c here and I have c here. So I can put one c on the right hand side. Right. So, so then I can put 1 over x to the other side, and I have implicit solution, which is 0 is 1 over x plus sinus of t. All right. So there will be an explicit solution that you have to solve. I explain again from the beginning. So in this case, we have dx over dt is x squared times cosinus of t. So in this case, the function on the right hand side is the product of x squared and cosinus of t. What we do is that we divide x squared to the left and we multiply dt. To the right, I'm going to have x divided by x squared is equal to t dt cosinus of t. I integrate both sides. So the antiderivative of 1 over x squared will give me minus 1 over x. The antiderivative of cosinus t will be sinus t, because I have to add a c, which is a constant. So I get an implicit solution, which is 0 is 1 over x plus sinus t plus c. So this is the implicit solution because I don't express x in terms of t, right? Now to find explicit solution, I'm gonna have to solve this equation. So I have minus 1 over x is sinus t plus c, meaning that 1 over x is minus sinus t minus c. So x will be minus 1 over sinus t plus c. So this is the explicit solution and this is the implicit solution. So in the exam or the homework, if you use implicit solution, it's going to be fine. And if you use explicit solution, it's going to be perfect. Right? So I explain again. So the key here is try to separate x and t. You separate that by dividing x squared to one side and multiply dt to the other side. So at the end of the day, you're going to have something of x on one side and something of t on the other side, because you have x and t split into two sides. You can do integration. So when you do integration, you get minus 1 over x is sinus of t plus c. All right? So this is going to be the implicit solution, right? So you don't solve x, you just put the relation of x and t, and that is fine. This is implicit, right? So meaning that when you solve this equation, you're gonna find x. But the better way is to solve it explicitly. So you're gonna solve x. 1 over x is minus sinus t minus c, and x will be minus 1 over sinus t plus c. So this is explicit because the form of x is explicit. So in the exam, you can use both explicit or implicit solutions. It's gonna be fine. Questions? It's clear? So let us, if there's no questions, let us go to another example. So I put this online. Could you see it? So I'm gonna. So I put the videos online and the lecture notes online. So now let us consider another example. So you have dx over dt is equal to x 1 minus x. Right, so this is example 1.3.2 in the book. So is it equation separable? Why?
Because you can multiply, you can put the x on one side and t on the other side.
Excellent. Can you say at the back of the paper, please? So this is separable because you can put x to one side and t to the other side, right? So what you do is you divide x 1 minus x to here, and you multiply dt to here. So what I have is x 1 minus x is equal to dt, right? So this is separable. So this is separable since x and t are in two different sides, different sides. All right. So this is a separable equation as well because you can split x and t into two different sides. Right. So what I do is I divide x 1 over x to the left, and I multiply dt to the other side. So what is the next step? Yes.
You integrate both sides.
Yes. Can you say it? Paper. So you integrate both sides. X 1 minus x, and this is dt, right? So the next step is simple, right? So once you have all of the variables separated, you integrate. So here you have x over 1 minus x, and you have dt. So what you do is you integrate both sides, all right? So what is this? So what is the, yes?
T.
Yes, can you say at the back? So this is going to be t. Of course, I always have a constant c over there. So the difficulty will be this guy. So how do I compute the antiderivative of 1 over x, 1 minus x? Yes?
Can't you separate it to be the integral of dx over x plus the integral of dx over 1 minus x?
Excellent. Can you say at the back of the paper, please? So the idea will be, so you're gonna write this as a over x plus b 1 over x. All right? So a, b will be the constant that we compute later. All right? So in order to compute a and b, how do we compute a and b? Yes?
The integral of a over x would be ln the natural log of the absolute value of x.
No, I want to see what is, how do I compute a and b? Yes?
You said it so that you said it so that x is whatever makes it 0, so you can solve for a and b. So you don't have 1.
Can you say at the back of the paper, please? All right, so you're going to have 1 is a, 1 minus x plus bx, right? So, all right, so this is equal to this, meaning that 1 over x, 1 minus x is a 1 minus x plus bx over x, 1 minus x, right? So this means that 1 is a 1 minus x plus bx. All right, so I'm going to set x to be 1 so that this is 0, and I'm going to set x to be 0 so that this is 0. So, I explained again before I set things to 0. So I have 1 over x, 1 minus x is a over x plus b over 1 minus x, and we need to compute a and b. We need to find a and b, all right? So in this case, we need to find a and b. So I have 1x, 1 minus x is a 1 minus x plus bx, x 1 minus x. Right, so this is the left-hand side, keep it to be the same. The right-hand side will be this guy. So now I can eliminate x 1 minus x, and I have 1 a 1 minus x plus bx. And now I'm gonna use the strategy that you said. I'm gonna set x to be 0. Now you set x to be 0. All right, so I have 1 is equal to a 1 minus 0 plus b times 0. So this is 0, this is I, and this is 1, so I is 1. Right? So I explain again. What I want to find are the two numbers A and B such that 1 minus x can be written like A over x plus B over 1 minus x. What I do is I keep the left hand side and the right hand side will be A1 minus x plus bx divided by this guy. I remove x1 minus x. I have 1 A1 minus x plus bx. So now I'm going to set x to be 0. When x is 0, I'm going to have 1 A1 minus 0 plus b times 0. So this is going to be 0. So this is going to be A, which means that A is 1. Now I'm going to set x to be 1 so that this is going to be 0. Right? So I have 1 A, 1 minus 1 plus b times 1. So I have b. So this is going to be 0 and this is going to be b. So in this case I have b is 1. Right? So therefore 1 over x, 1 minus x will be 1 over x plus 1 over 1 minus x. Alright? So I explain again. I have to find A and B such that I can split 1 over x, 1 minus x into two simpler terms. That is A over x plus B, 1 minus x. After I do all of this stuff, I get 1 is A, 1 minus x plus bx. Alright? So how do I find A and B? I just have to put this guy to be 0. Right? So I choose x to be 0. When x is 0, this is 1, so A is 1. This is the first thing that I found. The second thing is I'm going to put this guy to be 0, so I'm going to choose x to be 1. So when x is 1, b is 1. Right? So I have to replace x to be 1 here. I have A 1, 1, b 1. So this is 0, this is b. So I have b is 1. So finally, the A that I want to find is 1 and the b is also 1. Right? So which means that x, 1 minus x is 1 over x plus 1 minus x. It's clear? Now I'm going to use this formula. Now I'm going to erase everything and I'm going to put it back here. Right, so now I found that 1 over x, x minus 1 is 1 over x plus 1 over 1 minus x. So I have to integrate this guy, right? So dx, x, 1 minus x will be dx over x plus dx over 1 minus x. Right? So what is the antiderivative of x? Yes?
The first one will be the natural logarithm of the absolute value of x, and then the next one will be negative 1 times the natural logarithm of the absolute value of 1 minus x.
Thank you. Can you sign and the back of the paper, please? So this guy is going to be log of the absolute value of x, and this is going to be log of 1 minus x. All right? It's good. So I explain again. So to compute the dt, this is standard because this is the antiderivative of 1. This is t plus a constant c. So on the left hand side, I have to find the antiderivative of this guy. So this is going to be, I can write that like 1 over x plus 1 over 1 minus x. All right? So I take the antiderivative of the first guy. It's going to give me log of absolute value of x. The second one is log of 1 minus x. So then I'm going to have, I put things together, I have log of x minus log of x minus 1 is equal to t plus c. So this is implicit solution. Alright? So the implicit solution will be like that, right? So I don't have to solve x. I just leave it there. But I have to go to the next step to see what is the form of x, and this is going to be the explicit solution. So explicit solution. All right, so now I have to solve for x. Solve for x. So for this guy, I'm gonna have log of x divided by x minus 1, right? Is t plus c. Right, so log of a minus log of b is log of a divided by b. Right, so now, so after doing the separable, I found an implicit solution where x is not solved, but I still have a solution. Now I have to solve for x, which is explicit solution. So the first thing that I do is I use the formula log a minus log b is log a over b. So I have log of x over x minus 1 is t plus c, right? Now what I do is I'm gonna put e to the both sides. So I have x minus 1 is e to the t plus c.
Shouldn't it be 1 minus x?
So the absolute value of, yes, this is a good question. So absolute value of x minus 1 is absolute value of 1 minus x. So, yes. Other questions? It's clear? It's fine. Right? So, yes, so here I just changed 1 minus x to x minus 1 because the absolute value they're the same. Right? So, so now I have log of x over x minus 1 is t plus c. So x over x minus 1 is e t plus c. Right? So now I have x over x minus 1 is e t plus c. Right? Meaning that this is going to be plus or minus of this guy. So I have x over x minus 1 is plus or minus e to the t plus c. Right? Because the absolute value of this guy is e to t plus c, so this guy should be plus or minus e to t plus c. Now I have to solve for x. So, so in this case I have x is plus or minus e t plus c x minus 1. Alright? So I have to solve for x, so I multiply x to the right hand side. I have x is plus or minus e to t plus c x minus 1. And now I have x is plus or minus tc x plus or minus etc. This is because plus or minus minus 1, so I have minus or plus. Alright? So in this case I have x 1 minus or plus et plus c is minus or plus et plus c. Alright, so then x will be minus or plus et plus c dividing by 1 minus or plus et plus c. And for it this way, is it clear? Or you want me to do with both cases plus and minus? Okay, so let me. So this is something that I try to put plus and minus together. So in a separate way of writing, it's gonna be like this. Case number 1. So here I have x over x minus 1 is e to the t plus c. So x over x minus 1 will be plus or minus e t plus c, right? So I consider two cases. Case number 1, x over x minus 1 is e to the t plus c. So this is case number 1. So this means that x is e t plus c times x minus e t plus c. Alright, so this gives me x 1 minus e t plus c is minus e t plus c. And so this gives me x t plus c. Right? So I expand again. So after I do all of these things, I found the absolute value of x dividing by the absolute value of x minus 1 is e t plus c. Right? So which means that the absolute value of x over x minus 1 is e t plus c. Alright? So which means that x over x minus 1 will be plus or minus e t plus c. So this is the short way of writing it. But the long way should be the following. The first case, x over x minus 1 is et plus c, which means that x is et plus c times x minus et plus c, right? Because I multiply x minus 1 to the right hand side, right? So now I'm gonna put x to the left hand side, so I'm gonna have x1 minus et plus c is minus et plus c, right? So I divide 1 minus et plus c, and I get x is minus et plus c over 1 minus et plus c, right? So now case number 2, x over x minus 1 is minus et plus c, right? So this gives me x is equal to minus et plus c, x minus 1. So in this case, x is minus et plus c times x plus et plus c, right? So I'm gonna put this to the left hand side. I'm gonna have x1 et plus c is et plus c. So x is going to be et plus c divided by 1 plus et plus c, right? So this is the two cases in which you have the plus and you have the minus, and or you can write it this way. So you can put the plus and the minus together and you write it this way, or you can write it this way. This is going to be the same, right? Questions? Is clear? So basically, for separable equation, the key idea is that you split the x and the t to two sides and you integrate. So after you integrate, you're gonna get a relation between x and t. This is the implicit solution. So the implicit solution is fine. So you can put the implicit solution in the test and the homework. You're gonna get a full score. But it's better if you keep doing it and you find explicit form for x. For instance, for this case, you have two forms. This guy, or this guy, or you have one unified form like this, where you put a plus and a minus together, right? Questions? Yes?
E to the power of anything is positive, right?
Yes. E to the c is always positive. E to the alpha is always positive. For all alpha.
So does it matter if you have the plus and minus?
Nah, it's matter because here you have minus minus, here you have plus plus. So there are two different functions, right? Right, so this is positive. This is true. This is always positive, but this guy is not positive. X over x minus 1 can be negative, right? So this is why I have to put plus and minus, right? So this is like this. X over x minus 1 is 1. 1 is a positive number, of course, because it's 1. So now x minus 1 can be plus or minus 1, right? So this guy is positive. It's like number 1 here, but x over x minus 1 can be negative. So you have to put plus or minus, right? Yes.
So since we have e to the power of t plus c, is it possible you could separate it so it's e to the power of t times e to the power of c, the constant, and then
Yes.
just change e to the power of c to a separate constant value?
Yes, yes.
That would absorb the plus and minus values?
Yes, excellent. This is a very nice observation. Yes, thank you. Can you say at the back of the equation, please? So here I have two expressions, right? But there's a better way, right? So e to the t plus c is e to the c, e to the t, right? So c is any constant that we can choose. So I put this to be c tilde et. All right? So this c tilde can be, this c tilde is positive, right? So now in this formula, it's going to be minus c tilde et over 1 minus c tilde et. So this is this formula, and this is this formula. So you have c tilde et over 1 plus c tilde et, right? I explain again. So e t plus c will be e to the c times e to the t. So e to the c is a constant. It doesn't matter if I call it c tilde, right? So if I use this c tilde notation in the first formula, I'm going to have x is minus c theta et, and 1 minus c theta ec. The second one will give me c theta et over 1 plus c theta ec. Right? But this is going to be equivalent with putting this. All right? So the first one is going to be equivalent with putting minus c theta over c theta, minus c theta. Right? So I can put this to be c theta. And c theta, in this case, takes a negative sign. Right? So the general solution is of this form, where c theta can be both negative and positive. Right, so this is a very good remark, right? So you can observe the e to the c by a c theta. C theta, in the first case, take the negative value, and in the second case, is take a positive value. So you can put everything into one formula, c theta et, 1 plus c theta et, where c theta can be both negative and positive constant. It's clear? Questions? All right. So this is very good remark. So all right. So let us go to a theorem. Theorem 1.4 existent and uniqueness theorem. All right, so I'm gonna state this theorem, but I'm not going to prove it because the proof is very heavy. So it's required some functional analysis. And for our class, I think it's better that we focus on the computation. I mean, to understand how to solve the equation rather than going to the theoretical science of those equations. So in this, so this is section 1.4 in the book. So what we have is the following. So we have a function given an equation. So you have dx over dt is equal to ftx, and x0 is x0. So this is initial condition. Again. All right. So do we have a solution? To this equation, right? So if I give you an equation, the first questions that should come is that if there's a solution, right? So it's always like that. Do we have a solution for this equation? Right. So this is the existent. This is the existent part of a solution, of the theory of a solution, the theory of an equation, right? So do we have a solution for this equation? So who can guess what is the second question? Yes.
Is the solution unique?
Yes. So can you sign the back of the paper, please? So the first question should be, do we have a solution? And the second question should be, how many solutions do we have? The solution if exists, if is the solution unique, meaning that there's only one. one and only one. Right? So the first question should be, can we find a solution for this equation? Does it make sense to solve this equation? If there's no solution, why should we solve it? All right? So this should be the existent part of the questions. The second one is, okay, suppose that I find a solution. How many solutions can you find? Right? So is this solution unique? Meaning that if this is the one and only one solution of this equation, and this is the uniqueness part. Right, so in the theories of differential equation, these are the two most basic questions: the existence and uniqueness. Right, so this is also called the Cauchy theory. The Cauchy theory of an equation. Right, so when you look into an equation, the first thing you ask is if there is a solution, and if the solution is the only one that you can find, or is it unique? So the existence and uniqueness questions of an equation will form the Cauchy theory of an equation. So the Cauchy theory means existence and uniqueness, right? All right. So now let us look into this equation. So I'm gonna state the theorem. Any questions on this explanation? It's clear? Right. So let me state the theorem, and I'm going to show you some example. So let me put this with T0 to be general. So the initial condition can be any time, right? So if the first thing is ft is continuous. Right, so in both t and x. Number two, df x over dx, dx is continuous in both t and x. Then the equation I call this to be 1 as a unique solution. For t in R and x in R. For all t and for all. All right. So, I explain again. So if the function, so if we look into the equation, and if we see that the function f is continuous in both x and t, and the derivative in x of the function f is also continuous in both x and t, we can say that this equation has a unique solution, which means that you have a solution and this is the only solution of the equation without solving, right? So the theorem, so the meaning of the theorem is that, the meaning of the theorem, so we can look into the form of ftx and know if there is a solution, and if this solution is unique without solving. All right. So the meaning of this theorem is that, okay, you don't have to solve. You just look into this function f. If you see that this is a continuous function, the first criteria. The second one is that if the derivative in x of this function is also continuous of t and x, then you know that there's a solution. And this solution should be unique. You don't know what this solution is. You have to solve it to have the explicit form of the solution. But you know that this solution exists, and this is the only solution that you can have for this equation, right? So the theorem is powerful because you don't have to do all of the separable techniques that I just mentioned to you. You don't solve. You just look into that and you know in advance that there is the solution, right? So example. Any questions on this? It's clear? Example. Let us go to the example that we had before, which is so in this case, suppose that dx over dt is equal to I squared cosine of t. Right? So this is the equation that we have, and we have an initial condition, right? This is for t. So let us look into this equation. So my question is that you don't solve this equation. You don't have to do separable, right? So is there a solution for this equation? And if the solution is unique? Without solving. Why?
Because the function is continuing for both x and t, and then the derivatives, the functions are also both continuous.
Yes. Can you say at the back of this? So this equation we solve it in the film in the beginning of the lecture, right? But suppose that we don't solve this. So let's see if this has. Did you find the paper? So suppose that we don't solve this equation. Can we say that there's a solution, and if the solution is unique? So in this case, this is the f, right? So the ftx in this case will be x squared cosine of t. Right? So now let us check. So this is a continuous function in both x and t, right? So this is continuous in both x and t. First thing, so this is criteria number one. Criteria number one is that the function f has to be continuous in both x and t. So this is clear because you have x squared times cosine of t, and x squared is a continuous function, cosine of t is also a continuous function, right? The second criteria is dx of fxt. So this is going to give you 2x. So let me do it slowly. So this is going to be dx of x squared cosine of t. Right? So using the second criterion, I'm going to take the derivative in x of this function. So I'm going to take the derivative in x of x squared cosine of t. So this is going to give me 2 cosine of t. So 2x is a continuous function, and cosine of t is also a continuous function. So this is continuous in both x and t. All right? It's good. Which means that this is satisfying. So 1 and 2 are satisfying. So the equation has a solution, and the solution is unique. All right? So you don't have to solve. So we know this, we don't have to solve. The equation. All right, so we don't have to solve, we just look into the form of f, and we know in advance that there's a solution. and the solution is unique, right? So the second example is the one that we also solved a few minutes ago, which is dx over dt is x, 1 minus x. X3 is equal to 5. All right? So this is also the equation that we solved, but we didn't solve it with the initial condition. So my question is, if you don't have initial condition, is the solution unique? Yes?
No, because when you integrate, you'll have that constant.
Right, right. Can you say at the back of the paper, please? So without the initial condition, when you integrate everything, you still have the constant, right? So initial condition is designed for you to solve the constant. And when you solve the constant, you have only one solution. But if the constant is still there, you can put anything into the constant, then you don't have a unique solution, right? So now let us consider this equation that we solved before. We have an initial condition, right? So the initial condition is important because it's showing you that there's it gives you the constraint such that you have only one solution. So now, so this ftx in this case will be this guy. So is this? I mean, do we have a unique solution for this equation? And why? Yes.
The function is continuous in both x and t, and when you take the partial derivative of that function in terms of x, that will also be continuous in both
Yes.
x and t.
Can you stand the back of the paper, please? So this function, right, ftx is continuous in x and t, right? So there's no t, which means that in terms of t is a constant. So this is continuous in both x and t. So dt, dx of f will give you 1 minus 2x. And this is also continuous in x and t. Right? So when you take the derivative in x of this function, you get 1 minus 2x. Right? So because you take the derivative of x, 1 minus x prime, you're going to get x minus x squared prime. And this is going to give you 1 minus 2x. Right? So when you take the derivative in x of the function f at tx, you're going to get 1 minus 2x. So this is continuous both x and t. Because 1 minus x prime will be x minus x squared prime, and this gives you 1 minus 2x. All right? So in other words, the two criteria 1 and 2 are satisfied. So this function has a unique solution. So this equation has a unique solution. Right? Right? So you don't have to say that this equation has a solution and the solution is unique. You can say that this equation has a unique solution. And this is good. So we still have 1 minute. So let me. All right. So now suppose that I have dx over dt is the absolute value of x 1 minus x. X3 is equal to 5. Suppose that I put an absolute value into the function x 1 minus x. Does this equation has a unique solution? This is continuous, right? This is continuous. ftx is continuous, so this is good. So can we say that there's a unique solution for this equation? So we can continue this on Tuesday. So yes. So the answer is that we cannot say we cannot say anything about this equation. So this theorem says that, okay, if f satisfies these two conditions, you have a unique solution. But for this one, the second condition is violated because the derivative in x of this guy doesn't exist, and x is equal to 0 and x is equal to 1. Right? So the derivative in x doesn't exist at 2 points, 1 and 0. So the theorem is violated, but we don't know. So which means that we cannot apply the theorem, but when we cannot apply the theorem, it doesn't say that the equation doesn't have a unique solution, right? So in this case, you don't know. I'm going to explain this on Tuesday, next Tuesday.